So we were revising alkenes. I told you that now alkenes were very relevant to A2 because benzenes kind of resemble what alkenes are. So we talked about the reactions. We talked about Sp2 hybridization, where I told you that carbon would bond with 3 atoms, and the fourth orbital of carbon, the fourth electron of carbon, would end up forming a pi bond with the neighboring carbon atom. So each carbon atom would be fan-shaped, 3 bonds. This one would be making 3 bonds as well. The fourth electron of each carbon atom, they would overlap above and below, and they would end up forming a pi bond. And we talked about electrophilic addition last time, and I told you that the pi bond has a very high charge density. I told you that the electron cloud is really concentrated. It's got a large polarizing power. I mean, it can repel the electrons of the bond over here between the bromine molecule, and so no special conditions are needed. I mean, that's something that's very important. I'm going to highlight that that the polarizing power was very, very strong, which is why you never needed any special conditions for bromination. And the bromine molecule would get polarized, and the positive bromine will get attracted to the double bond. And in the next step, the Br-1, which is last, would be attracted to the carbocation to form, to complete the bond. And there was a Markovnikov's rule, which was for unsymmetric alkenes. Now, this one was specifically for unsymmetric alkenes that now for unsymmetric alkenes, I told you that you had 2 possibilities that I mean, the H and the Br have choices. The H could bond with this one and the Br could bond with this one, or the opposite, which is the H could bond with this one and the Br could bond with the one on the right. So you had 2 options. And I told you that the H likes to bond with, I mean, I didn't write the Markovnikov's rule. I should have, I mean, the Markovnikov's rule was that the H atom likes to bond with that carbon atom so it likes to bond with the carbon in double bond in C double bond C that is already bonded to more carbon atoms. That was what the Markovnikov's rule was. So you would get 2 carbocations. The positive H would bond with the double bond, and it might bond with the carbon on the right side. The other carbon atom would become a positive, or the H might bond with the carbon on the left, and the other one would become positive. This positive carbocation had a much larger positive charge because it wasn't surrounded by large groups. So what would happen is that forming this carbocation was kind of difficult. This was unstable. Why? Because the positive charge is so large that the H is not able to pull the electron away from it. I mean, this electron over here that the H got from the double bond, the H will not be able to do that. But over here, if H bonds with this carbon atom on the right, H will be able to pull this electron away from the double bond over here. Why? Because the positive charge formed is going to be small. And the reason it's going to be so small is because it's surrounded on both sides by carbon chains. And these carbon chains have lots of electrons. So those electrons would flow towards it, and they would kind of neutralize the positive charge. So the positive charge is not going to be very strong. It's going to be smaller in size, which is why the H would be able to pull the electron away from it. So carbocation that has more alkyl chains, which are electron donating, positive charge density decreases. So the carbocation is considered to be more stable. And this is the more likely carbocation. Okay, which is why this is the major product. Is this all clear?
Yes, sir.
Okay. So that's all about alkenes. Now what we're going to do is we're going to move towards benzene. We're going to start talking about benzene. And remember this thing, the important thing is, before we discuss benzene, I'm going to stress this simple point over here. This one is the most important point over here, the one that's right over here. I'm going to make two boxes around it. Okay, remember your pi bond over here has very high charge density. It's got a very high polarizing power. And this is something that would be different in benzene. Now, first thing is, what is benzene? Now, benzene is this thing. You often see it as this thing. It's got it's a hexagon with a circle in the middle. Okay, that's what a benzene is. That is the skeletal formula of benzene. Okay, that's your skeletal formula. And the other forms of benzene, I mean, this the other type of formula that benzene is going to have is this one. Like the structural formula, it's going to be 6 carbon atoms in a ring-like structure with each carbon atom bonded to an H. And there's going to be a ring in the middle. Okay, so there's going to be this ring-like structure that's going to be right in the center. So, I mean, both of these things are the same. This is the structural formula, that's the skeletal formula. So the issue is, what is this thing? Another way to actually think about this is, if you can imagine carbon, I mean, there's another simplified version that kind of makes a lot more sense. And it's this version where the double bonds that you have 6 carbon atoms with alternating double bonds. And each carbon atom is making the 4th bond with NH. Now, this is known as a cuculus structure. This one is not used by CAIE. Okay, they don't use it. Cambridge doesn't use this, but that's your cuculus structure. But that makes a lot more sense because you're aware of double bonds, because this ring doesn't really make much of a sense. So it's basically double bonds, alternating double bonds, and these double bonds kind of get mixed up. What the ring represents is delocalized electron cloud. As the pi bond electrons get delocalized in the double bonds. So basically all your double bonds kind of get mixed up, which is why you get this delocalized electron cloud. And I'm going to show you how that happens. First thing is, can you tell me what type of hybridization is this when carbon makes or bonds with
Sp2.
Okay, that one is Sp2. So that means carbon is only bonded to 3 atoms. So I'm going to draw the structure now, the detailed structure of benzene. So carbon is bonded to 3 atoms. So that's 1. You got another one, and each carbon atom is bonded to just 3 atoms. Then you have the next carbon atom that's going to be bonded to 3 atoms as well. So the next one is bonded to 3 carbon atoms. Then you have the next one, and that would also be bonded to 3 carbon atoms. And then you've got 3 carbon atoms. This one will have a carbon atom. There's going to be a carbon atom here. So here are your 6 carbon atoms. All of them are sp2 hybridized. And let me just, so all of them are sp2 hybridized. And just a second, let me. As anyways, one second. So true. That's fine. So each one is sp2 hybridized. That means if you look carefully, this one is an sp2 hybrid orbital. This one is an sp2 hybrid orbital. This one is also an sp2 hybrid orbital. These are your H atoms that it's bonding to. Just 1 second. Sakib, at the moment they're all single bonds. Okay. Now we did sp2 hybridization. This is what it looks like. Okay, we just did that. Then sp2 hybridization was that carbon's 3 electrons get pulled in different directions like a fan. The 4th electron is not doing anything. So that's what sp2 hybridization is. So carbon's 3 electrons, they get pulled in different directions, except the 4th one is not doing anything. So these are your sp2 hybrid orbitals, and they're all sigma bonds. There are all these sigma bonds that are formed. So let's just label them. All of them are going to be sigma bonds. And these sigma bonds are formed due to overlapping of sp2 hybrid orbitals in each case. Okay, so all of them are going to be your sigma bonds. This one is a sigma bond. This one over here is a sigma bond. Okay, so now the issue is what happens to the 4th electron? Each carbon atom has a 4th electron, but initially, no one is attracted to the 4th electron. The 4th electron is not doing anything. Okay, so each of your carbon atoms, they've got this 4th electron. And right at the beginning, this 4th electron is not doing much. Okay, so let me just get rid of this. So there's a 4th electron that's buzzing around, not doing much. Okay, not really doing much. And they would start overlapping, forming a pi bond. Now what happens is they're going to form, they can form 3 pi bonds. They can start overlapping with each other, and a pi bond is going to be formed. These two can start overlapping with each other, and that would result in the formation of a pi bond. Okay, so they're all overlapping. This one overlaps with this one, and they all start overlapping. That's your 3 pi bonds. Is this clear so far? Yes or no? Is this clear? Aruba, is this clear?
Yes.
Yes, sir.
So, but now the issue is, if these two are overlapping, why don't they all start overlapping? Like this electron over here, like if you focus on this electron over here, it's overlapping with the orbitals on the right side. So why doesn't it overlap with the orbital that's on the left side? It's going to do that. So eventually what happens is they all start to overlap with each other. These two orbitals, they would start overlapping. Okay, so these ones over here, they're going to start overlapping with each other. These ones over here, they're going to start overlapping with each other. And as a result, all p orbitals, they overlap, and a delocalized pi electron cloud is formed eventually. So is this thing clear? That you have a ring of pi electron cloud above and below.
Yes, sir.
Okay, so you've got a ring of pi electron cloud above and below. Okay, and let's list all the properties, because there've been questions where there've been big questions where they've asked you to describe the whole structure. So we're going to talk about the carbon atom being sp2 hybridized. We're going to talk about the angles. Bond angles are 120 degrees because each carbon atom is fan shaped. And it's going to be a planar molecule. It's going to be a completely, it's like fans, lots of fans joined up. That's one carbon atom, that's a fan. There's another fan over here. They're all lying flat. So it's a completely flat molecule, just two-dimensional. This carbon atom, so it's a completely flat sheet-like structure. The electron clouds above and below. So it's a planar hexagonal molecule, completely flat. All the angles are 120 degrees. Each carbon atom makes 3 sigma bonds. Okay, those are all the properties of this thing. Now, there's one issue. This is similar to what happens in alkenes as well. Like in alkenes, you kind of have the same thing. Like in alkenes, we drew the molecule of an alkene, but in alkene, you just had 2 carbon atoms. You just have a carbon atom making 3 bonds, 3 normal sigma bonds, and the 4th electron gets it ends up forming a pi bond. So that was what an alkene was, but the electrons were all concentrated at a very specific point. The electron density was high. We wrote that down as well. I told you that in a pi electron cloud, it's got a high charge density. The electrons are really concentrated at a particular point. But in a benzene structure, what happens is that the electrons that were over here in this orbital over here, not only were they overlapping on the right side, they were also overlapping with the atom on the left side. So that means the electrons are distributed over a much wider area. And that kind of indicates that the electron density is much lower than a normal pi bond in an alkene. Is this point clear as well?
Yes.
So electron density is lower compared to pi bonds in alkenes. Alkenes, as electrons are delocalized over a much bigger area. So this thing, this bond that's formed, that's somewhere between a double bond and a single bond. Okay, so you have single bonds between carbon atoms. You have double bonds in alkenes. Benzene is somewhere in the middle. Benzene is, it's got a solid single bond. That's a single bond, but the electron cloud over here is kind of distributed. So it's much lesser. So the benzene is somewhere in the middle. So benzene is stronger than a single bond, but it's weaker than a double bond. This is strong, while this one is weak. Okay, so you've got a weak, single bonds are weak, double bonds are strong, and benzene is somewhere in between. It's somewhere between a single bond and a double bond. Is this also clear? Okay, clear?
Yes,
Yes.
sir.
And we can also have a look at, even in the data booklet that's this is given, maybe that you get an energetics question related to benzene. So if you ever were to meet a, like if you had to break the bonds in benzene and they were looking for energy, so they used to be, I don't know if this is the right data booklet, but this one, I mean, you can see over here, this one, you've got single bonds, you've got double bonds, and you got triple bonds as well. But then there's this benzene, that's a single bond with a dotted line on top. And this one is somewhere between, it's stronger than a single bond, but weaker than a double bond. So if ever you had an energetics question where you were supposed to break the bonds in the benzene, remember that this is what the bond energy is going to look like. TK, is this also clear?
Yes.
So now what we're going to do is we're going to start with the first reaction of benzene. Okay, that's a benzene. That looks like an alkene, but it's not really an alkene. It's kind of different from an alkene. It's a separate functional group. Okay, you have to remember that as well. It's not a benzene is a completely separate functional group. So we're going to do the first reaction. The reactions of benzene. Yes.
Sir, is benzene soluble or insoluble?
Nee, it's so you tell me, soluble in what?
Water.
So water makes what type of bonds? Intermolecular forces. What are the intermolecular forces in water?
Hydrogen bonds.
Okay, so benzene is a non-polar molecule. Okay, I mean, carbon and hydrogen bonds are kind of non-polar. So it's not going to be very soluble. It's probably going to be insoluble. Okay. Is this clear?
Yes.
It is soluble in non-polar solvents. Because this is a non-polar molecule. Okay. अच्छा लेकिन होता ये कि what actually happens is कि when molecule size becomes bigger, remember hydrogen bonds are really strong. ठीक है, hydrogen bonds, I mean the polarity is really strong. What happens is, I mean this is although non-polar, but what happens is that when a molecule becomes bigger in size, its van der Waals forces, they keep on increasing. So the van der Waals forces, I mean, the electrons might get knocked to one side. For example, over here, the electrons, like there might be a collision and the electrons get knocked to one side, right? So this becomes negative and this becomes positive. Like molecules are all constantly bumping each other, okay? So the electron cloud is not going to be evenly or perfectly distributed as shown in this picture over here. The molecules are bumping around. So van der Waals forces is the electrons might get knocked to one side. This side would become negative. So in van der Waals, what happens is if the molecule size is really, really big, the negative charge is really strong. And if the negative charge is strong, then it might start attracting the water molecules as well. But that only happens for very big molecules. Like if, is that point also clear? Is this clear or not?
Can you repeat one more time? Sorry, I don't understand. The charge, I don't understand.
I was just saying that, I mean, this one is a non-polar molecule, right? So that means it's not going to have any polarity. It's not going to have any partial negative or partial positive charges, right? But is that part clear?
Yeah.
But it's going to have van der Waals forces. There's going to be some fluctuation going on. There would be some fluctuation that the electrons might get knocked to one side or get knocked to the other side during collisions. Is that clear?
Okay. Yes.
So if they get knocked to one side, this side would become slightly negative. This side would become slightly positive, right?
Okay.
And in the next instant, the electrons might, these are instantaneous dipoles. So in the next instance, the electrons might get knocked to the other side, which this side would become negative, this side would become positive. So, I mean, there would be random dipoles being created. That's what van der Waals forces is. Maybe the next second, the electrons get knocked in this direction. So this side would become negative, this side would become positive, right? So there would be random dipoles being created. I was just saying that as the molecule size keeps on increasing, the dipoles, those instantaneous dipoles, they become stronger and stronger. And for very big molecules, they kind of start attracting water molecules because the instantaneous dipoles are strong enough to attract the water molecules. Like the bigger the molecule, the more electron it has, the more random fluctuations would happen. And the instantaneous dipoles would kind of become stronger and stronger. Bigger molecules have more van der Waals forces. Is that clear?
Yes, sir. I got it.
But anyways, it's not really going to be soluble because it doesn't form hydrogen bonds that much. So not very soluble. But anyways, I was talking about the reactions, and we're going to start talking about the reactions. The reactions are the first one. I'm going to write down the reactions, both of them. And then we're going to talk about the mechanism of the reaction. So the reactions are known as electrophilic substitution. Okay, so these are known as these are known as electrophilic substitution. The first reaction number one is known as bromination or chlorination. I mean, it is electrophilic substitution. What happens in that reaction is you've got a benzene. And so you have a benzene and it's going to have a ring in the middle. And you react it with Br2. And a substitution reaction happens. If you add a catalyst, it's going to be FeBr3 catalyst or AlBr3. Bromination needs a catalyst in this case. And once you add a catalyst, so once you add a catalyst, one of the H atoms, let me draw the H atoms. There used to be H atoms, there would be 6 of them. So what's going to happen is one of the H atoms gets substituted by Br. And the H that is substituted would bond with the other Br and form HBr. Okay, that's your bromination reaction. The chlorination reaction would be kind of the same, except with chlorine and with a different catalyst. So the chlorination reaction is going to be exactly the same. You're just going to have Cl2 instead. And the catalyst would be the same ones except for with Cl. So it's going to be FeCl3 or AlCl3 catalyst. And instead of bromine over here, you're going to get HCl as a byproduct. Because that's a substitution reaction. The Br comes in and replaces the H. Yeah, that's the reaction. And there's a second one, and that's known as nitration. So we're just going to write that reaction. Okay, that's a nitration reaction. But let's leave it here. Okay, we'll do the first substitution reaction, and we're going to discuss the mechanism of this electrophilic substitution. Okay, the mechanism of this. How does this happen? Why do you need a catalyst? Like, you never needed catalyst for alkenes. So mechanism for electrophilic. Substitution. So we'll continue with this. TK, we'll talk about and discuss these two reactions in detail. Let's do that tomorrow now, TK. Let's continue tomorrow. So, okay, everyone.
Hafiz. Thank you.
Take care, Hafiz.